Everyone. So the first speaker this afternoon is Jinchi from the University of Southern California, and he's going to speak about asymptotics of eigenvectors and eigenvalues for large structured random matrices.
Thanks. All right, good afternoon, everyone, and I want to thank everyone for staying here, and also thank Richard and all the conference organizers for the very kind invitation. It's my great pleasure to visit Newton Institute and give a talk at this wonderful workshop. I have really enjoyed all the talks so far. I'm sure I will enjoy the talks that are forthcoming. And actually, this workshop is reminding me of another workshop that was exactly 12 years ago, given that Yingying gave a talk about the recent developments in random matrix theory, and also Peter Bickel and Lisa Novina talked about the latest developments in networks. And and I also want to thank Peter for introducing the topic of networks to Yin and me when we were sabbatical 3 years ago. So it's a small world. And actually, today, what I'm going to talk about will touch a little bit about two fields. One is RMT, random matrix theory. The other one is networks. And we know both are really big fields. And for us, we wanted to ask two simple questions. First question is, we're trying to better understand the properties of something so-called eigenvector, which is a very fundamental concept from linear algebra. So more precisely, we want to understand the precise asymptotic distribution for eigenvectors. Second question was, how could we do hypothesis testing in networks? Because both RMT and networks are such big fields, I would say that essentially the hypothesis testing question we're trying to ask in this project is of nature that's new to the literature. So any comments, suggestions, and equally criticisms are welcome. And because in my family, actually my 5-year-old just doesn't agree with me. And recently, my 2-year-old tends to not agree with me. A particular reason is I'm actually the only LV in my family. So actually the talk is about the joint with Jianqing Fan at Princeton, Yingying Fan at USC, and Xiao, postdoc at USC, who is very talented. Because this is afternoon after lunch, so I put a nice painting. Hope you might enjoy. The main point is help you keep awake. And because myself actually is a terrible painter, and I really like the painting so much that I actually used the happy puppies for 3 talks. First one about knockoff inference. Second one about causal inference, and today, actually, I'm using the same puppies for network inference. If you like, you can call them happy network puppies. Actually, I'll start with a very simple, motivating example explaining what we're trying to do, and then I'll explain how we calculate the numbers. And after that, I'll explain in a very high level a general theory explaining what we did. Finally, I would like to conclude with some numerical examples. And feel free to stop me at any time. And for some reason, if I missed a question, you may speak up. You know, the world we live in these days, on one hand, is highly personalized. For example, if you talk about healthcare, we talk about treatment plan. Not only we care about whether the plan is effective for the average population, we want to make sure that the treatment plan is best for each of us, individual. At the same time, our world is also highly connected. For the happy puppies, they may communicate with each other, they play with each other. For example, every day we send emails to people for various purposes. Well, for this kind of examples, well, if you look at how people communicate, for example, just count how many emails sent to each other, and then you do a threshold. Whenever it's above a threshold, you put a coin there, which means the two are connected. otherwise put 0. And once you have this kind of data structure, you can ask lots of interesting questions. And we saw lots of studies in literature, including by people in the audience. For example, you can do link prediction, you can do community detection. But what I'm going to talk about today is different from those topics. The question you want to ask is, if you have individual A and individual B, we want to test whether the pair belongs to the same community. Of course, how to define the community is up to yourself. And I would like to start with a really classical example in networks. This is, for example, if you, the graduate student getting into the field, this is probably the 101 data set. It's so famous, so commonly studied. The University Karate Club data set by Zachary in 1977. And this data set involves 34 members of the club. So if you see a 1 connecting 2 people, that means the 2 hang out a lot outside regular club meetings, which means you see link 1. Otherwise, there's a missing link. The picture we see seen here actually is from the classical one, from the paper by Gerwin and Newman, 2002. Of course, these days, you can impose so many different models or algorithms, clustering algorithms, to come up with exactly the same picture. So if you look at the picture, the 2 essentially is color-coded. 2 clusters or 2 communities. One is centered around H, the other one centered around A. And particularly, if you, for example, if you look at number 7 and number 8, okay, number 7 and number 8, that belong to the H community. Number 9, number 10, number 27, that belong to blue or A community. So there's lots of algorithms that can give us the picture. But we want to ask a further question. As I just mentioned, we want to test each pair of nodes whether they belong to the same community, which means in addition to yes or no from clustering algorithm, we want to come up with these numbers, sometimes number between 0 and 1, the p-values, which means if you see small p-values, that indicates very strong significance, evidencing that the 2 might come from different communities. Okay. The question is, how could we get this kind of numbers? And we all know that it's the common wisdom of field that all models are wrong, but some are more useful than others. Just like linear regression model is still useful, but it's only an approximation to reality. The picture I just presented could be obtained by stochastic block model with non-overlapping communities. But I can argue that the model is a sort of starting point. And what if we use this model can be easily missimplified? And we know that model missimplification is real and it has implications. This has been studied in many years by many people. The question is, what if we switch to a different model? Let's consider the mixed membership models, which means with overlapping communities. In this case, we have a different picture, which means every node, presumably, they have basically 2 colors. So this is, you can call it a pure node, belongs to basically this community. But this one actually split between different communities. And once you move away, simpler model, you want to go with more flexible models. Of course, you and your friend might have different choices. The question is, if I have different models, presumably get different pictures. The question is, do we need a different test? Which means, suddenly I move from model A to model B. Do we need a new test? Presumably, if you need a new test, we have different results. The another question is, how can we make sense of different pictures, different model structures, and presumably different results from testing? And we all know from social sciences that the world we live in is actually much smaller than we thought. the something so-called 6 degrees of separation. And actually, for the word natural inference, actually it can be much simpler than we might have imagined. A nice surprise is, even if you move away from a simple model, you go with more flexible models, actually we can have the same test, which means we have same table, the same p-values. And we don't need to argue with ourselves which test should we use and which p-value should we interpret. The question is, how do we calculate the numbers? So put it high level, in this project, we're curious about two questions. First one is, can we come up with a tool for flexible network inference with precise p-values for testing whether two nodes might belong to the same community? Second question is, actually, the first one is on the network side. Second question is about the RMT side. The question is, can we better understand the behavior of eigenvectors and eigenvalues for larger unstructured random matrices? But still we face the issue that we could work with different models, which means different model structures might give us different results. What we would like is, can we do something so-called model-free? I have to be, we know basically we never use model-free. It's very risky. So this is loosely speaking, which means the inference result should be more general. Okay. So next, let me explain how we calculate numbers in the tables I just presented. Okay. So let's start with some very basic notation. Suppose we have a network with n nodes, 1 through n, and we can observe adjacency to the matrix X. Xij is n by n matrix. So this is 0 for no link, 1 for link. And this is very big field, and I put it here basically some more recent review articles. So basically, the adjacency matrix X, which is random, can be decomposed in two parts. H part is deterministic. It's more like non-random part, the mean structure. W part, actually, the noise. So the assumption here is we assume that all the diagonal and up diagonal entries, they're independent with mean 0, and in this setting, each entry is bounded by 1. And if you are familiar a little bit with the literature RMT, actually W matrix is often known as generalized Wigner matrix. And if you are from math side, and I have to say, when I use a term, it's loosely speaking. If you read the papers, RMT papers, when they define the generalized Wigner matrix, there's a bunch of mathematical conditions. So here, again, what I meant basically loosely speaking, which means the variance actually is heterogeneous. Which means Xij's, they're independent coin flips with probability Hij. As is common, we decompose the network into K communities, C1 through Ck, and for every node I, the node might belong to either of the K communities. Essentially, the probability that node I belongs to community Ck is called pi ik, which means for every node, we attach a k-dimensional vector. Those are probabilities, non-negative, sum up to 1. So in this work, we assume that the number of communities k is finite, that is unknown. So that means later on we have to estimate number. Getting back to the question I started, essentially, for every pair of nodes I, j, we're trying to ask whether I and j come from the same community. Since we're talking about mixed membership, it's a little bit ambiguous when we talk about which community are we talking about. So mathematically, although there's many possibilities, we started with a very simple form of testing. We test whether the probability vector for node I is identical to the probability vector for j. It looks like, for example, the simplex. The simplex, you want to see whether the 2 points coincide with each other. Alternative, they're different. And in order to derive some results or test, let's start with something concrete, which means we have to start with some model. So we start with mixed membership model. But our starting point here is we look at a mixed membership model, but we assume all the node degrees are homogeneous, which means for now, we don't need a degree heterogeneity because this can make things a little bit more complicated, which I'll come back in a second. So in this case, the expectation of the adjacency matrix H, the mean structure, is equal to theta, which is scalar, that can convert to 0, times pi is more like membership probability vector matrix, times p, the connectivity matrix within the blocks, and also pi transpose. The model was originally proposed by Erode, Bly, Feinberg, and Shin in 2008 JMLR paper. Okay. So naturally, if you go back to this pi vector, if you assume that this guy, of course, is on simplex. If you assume that all the pi i's can only be the vertices of the simplex, that reduced to the Stokastic block model without overlapping communities, which means every pi I has only one non-zero component, which is 1. Okay. So how do we proceed? So let's look at the mean structure, the eigen decomposition. It's V matrix times D times real transpose. D is the diagonal matrix of eigenvalues. But normally when we talk about eigenvalues, people, if you start with adjacency matrix, you can do lots of simple matrix operations, and you start analyzing the eigenstructure of the new matrix. Oftentimes, the eigenvalues are non-negative. But here, in this work, we start with X itself, which means the eigenvalues are real, but could be negative. So we look at absolute values. We rank them from high to low in magnitude. So this collects the corresponding eigenvectors. Because we don't know the population, we estimate the population parameters using sample. So X is what we observe. Let's look at the empirical eigendecomposition for X. So naturally, we have D hat, the empirical eigenvalues, and also empirical eigenvectors V hat. But again, these eigenvalues are not necessarily positive, which means we have to rank the magnitude. Okay. So without loss of generality, we can assume that this is basically in descending order of magnitude of the eigenvalues. Okay. So now the question is, I showed you a table of p-values. How do we compute the p-values? So here I want to explain the idea of something called ideal test statistic, which explains the intuition of what we did. So there's a very simple observation that if the two nodes do come from the same community, which means our assumption pi high is equal to pi j, then it's almost immediately you see that for the eigen matrix, the rho I must be equal to rho j. So such a simple observation. Then the question is, we can use observation to construct a test. Okay, so let's start with the blue guy, the ideal test statistic, Tij. So at the population level, if the null is true, they should be close. Then we're trying to find the distance between rho I and rho j from the empirical eigendecomposition. So essentially, here we have a quadratic form. Of course, we have matrix here. And what is sigma 1? Sigma 1 is covariance of this guy. Ei is the basis vector from Euclidean space with i's component 1, rest 0. The difference between Ei and Ej. And W is the generalized Wigner matrix I showed you a minute ago. V is population eigenspace. D is population eigenvalues. So this is why I call it ideal, because this is population parameters. But hopefully, we can see the insights much easier. Okay, this covariance matrix, if you invert this guy, let's call it Tij. Then the question is, what are the precise properties of Tij under null and under the alternative? So naturally, whenever we do theory, we have to work with assumptions. Actually, Jianqing doesn't like very complicated conditions, so is Yingying. And I'm happy that we're able to put all the conditions just one slide. So, loosely speaking, in some sense, this is a lucky project. I don't need to, for example, go through multiple slides. Just 3 conditions. Okay, so naturally, since we care about the eigenvectors, we have to ensure some kind of gap or separation between consecutive absolute eigenvalues, because by nature, eigenvalue could be non-negative. So essentially, we look at ratios. It's bounded by from below by 1 plus a little constant. This one parameter after n is maximum row sum of variance of this the noise matrix. And then we have some conditions on the lowest eigenvalue of the pi transpose times pi. Essentially, it's more like the bound on smallest singular value if you look at a pi matrix. And smallest singular value for the p matrix. And also, the network cannot be too sparse. Otherwise, we'll have intrinsic difficulties. And last condition is the eigenvalues of this matrix should be bounded away from 0 and infinity. Yes?
How does this translate into every degree?
Yes, right. So essentially, because right now we're looking at a very, very simple model. It's a mixed membership model without the degree heterogeneity. And essentially have the parameter theta, pi, and b. And it can go back and you can check the growth of the degrees.
So
yes.
is it polynomial in n or log n?
Actually, that will be clear.
Looks like polynomial in n.
So essentially, yeah. To simplify the result, I'm going to mention the theorem. Essentially, we want to make sure the asymptotic power converges to 1. In that case, we have to make sure that the average, no degree, should be diverging. And if you look at the rate, it actually is a little bit faster than log n rate. So it means n to the power epsilon, but epsilon can be arbitrarily small. And also, I want to say that because this is initial efforts, all the conditions I'm stating here presumably could be highly non-optimal. Yeah. Okay. With the assumptions I just mentioned, we can derive the behavior, the distribution of the test under the null and alternative. First one is under some conditions, we can show that if node I and node j come from the same community, and turns out Tij asymptotically converts to a very simple distribution, chi-square with k degrees of freedom. An alternative, this mirrors actually the power. If pi I and pi j are not identical and not too close to each other, the rate controlled by this guy, then asymptotically, the power can go to 1. And for simple case of stochastic block model with non-overlapping communities, because we start with overlapping communities. But if you get back to the simple case, and you can basically plug in these numbers, and you see basically it's better to see how the rates kick in. But what I just mentioned is something ideal because it involves population eigenstructure, which we can never observe in real life, which means it's not applicable. So there's 2 things we have to pay attention to. First one, k. We don't know k in practice. We have to estimate. Second one, in the quadratic form, it involves precision inverse of sigma 1, which we don't know either, which means we have to estimate. So theorem 2, at this stage, actually is a little bit straightforward, of course, with some efforts. If our k hat is consistently estimated for k, which means with asymptotic probability 1, our k hat is equal to k, and if our covariance estimator is well behaved, this is 2 norm. It's consistent with certain rates. All the results we saw from previous slide are true. But we need these assumptions. The question is, can we achieve this? And luckily, in this setting, we have ways to estimate parameters. But in simple term, k hat, we can just simply threshold the empirical eigenvalues, of course in absolute value. Whenever it's bigger than certain threshold, you keep. You count how many. And turns out, we can show that the k hat is consistent estimator. But for the second guy, it's much more complicated, which means we have to estimate sigma 1. And sigma 1, the formula is a little bit complicated. But if you remember a little bit from the previous slide, actually sigma 1 depends on the noise matrix. Then the natural idea is just like in regression, right? How do we estimate error variance? You run the lateral regression, and you work with residuals, you estimate the variance. Similar idea here. We do eigen decomposition, and we subtract the low-rank structure. We have residual matrix. We can estimate. But reality is much more complicated than I just said. Turns out we have to do several layers of tricks in order to get a good estimate for sigma 1. In the end, the conditions hold, which means in real life, we don't need to know k, we don't need to know sigma 1, and we can get the precise properties. So by now, I explained how to calculate the connections among these happy puppies, whether two puppies, they belong to the same group, how to calculate p-values. And you might ask the question, because what we just started actually is using a relatively simple model, because we assume that the nodes, all the nodes have homogeneous degrees. But in real life, we all know that the world is highly heterogeneous, which means how can we deal with degree heterogeneity? Well, in this case, we can work with more general model, and the degree corrected mixed membership models originally proposed by Zhang, Lavina, and Zhu in 2014, and also later analyzed in a paper by Jing, Ke, and Luo. So the trick is you replace a identity matrix, a matrix that is proportional to identity matrix by a diagonal matrix. So every node has its own parameter theta I. This guy characterizes the degree heterogeneity. So naturally, if you want to do testing, because they have different models, they'll be different. But at the philosophical level, as long as we can deal with heterogeneity, the ideas I just mentioned should carry through. So a short summary is, a new test statistic Dij is very similar to, in flavor to what I just mentioned, of course different forms. So after you go through some efforts, we can show that even if we have node heterogeneity, we still have the same asymptotic distributions. So what I just presented actually is a very short summary of what we did in network inference. And we're still wrapping up the paper. Essentially, in the paper, we have more comprehensive theory. And probably noticed that by this point, I only provide you a very simple table. And we have additional numerical examples from paper and studying the size and the power of test. And looks like finite sample property is pretty nice. Okay. So by this point, and we know that for a network, we can test whether they belong to the same community, and you can calculate the p-values, and it's pretty flexible in terms of network structure. Then we are curious about one question. What's the key tool that power the theory for flexible network inference that we did? Is there anything special or anything general? And turns out there is a general theory behind what I just presented. And also, I feel a little bit nervous when I use the term general. The general actually is here is relatively general. Yeah. Okay. So to make sense of what I just mentioned, what do we mean by general theory? Let's start with some model setting. So essentially, in this part, we're trying to understand the behavior of spiked eigenvectors and eigenvalues for large structured random matrices. From this point on, I want you to forget about all the network models I just mentioned. So no longer working with mixed membership models. But we need some structure. And we need a spiked model, spiked the structure introduced by Ian Johnston in a series of work. And we consider a wide class of random matrices symmetric. And by the way, RMT is a very, very big literature. Actually, when I was writing my thesis, in order to finish my thesis, actually, I had to read the literature RMT. So I was starting reading papers from years back. But these days, there's very good review articles and books and more recent papers, summaries on the topic. But for the random matrix consider, it's very general. X is mean structure, which is low rank, plus W is generalized Wigner matrix, which means they have heterogeneous variance. Again, let's look at the population structure. The low rank part basically means has eigendecomposition against D and V, same as what we saw earlier. And for the noise matrix W, similar structure. So basically, all the entries on the diagonal and above diagonal mean 0, and this is bounded. Actually, we work with assumption to simplify our technical arguments. And if you like, you find that many models we used for networks, for texts, such as copy models, fall in this category. Okay. So this is the population eigenstructure D and V I mentioned, which come from the low rank structure. But in real life, we don't know those. So we estimate from data, which is the matrix X we observe. So we look at its spectral decomposition. Again, lambda 1 through lambda n, this is the empirical eigenvalues. V hat 1, V hat n, these are the empirical eigenvectors. And again, the spikiness here is a little bit different from what people usually talk about, for example, in covariance model. Because for covariance matrices, the eigenvalues are non-negative. But in our case, it could be positive, also could be negative. That's why we look at absolute values. We rank from high to low. Okay, without loss of generality, we assume that we rank in this order. And if we take out the top k columns, this is exactly the spiked eigenvectors. Okay. As I just mentioned, we are curious about the behavior of lambda 1 through lambda k, and more importantly, the real motivation for our project was trying to understand this guy, V hat 1 and V hat k, because we know that RMT is such a big field, and if you read the results and the papers from RMT literature, you find a very nice thing. Majority results are about the behavior of the eigenvalues. Well, there's so many semicircular law and MP law, and also the universality results. But when it comes to eigenvectors, the results are relatively limited. And of course, if you know the RMT literature relatively well, and we know that in the RMT literature, if you consider covariance matrix estimation, there's some results about eigenvectors, which is not our focus today. But if you look at results from that literature, they make assumption that to understand the behavior of this guy, they come out with a very special linear combination using the population eigenvector. For example, V transpose times V hat. The results rely on this kind of weights. Of course, in real life, we never know the true guys. Okay. How do we proceed? I have to introduce a little bit of mathematical concept here. So essentially, if you have a pair of unit vectors, x, y, so x and y actually here are not random. It's any unit vector from Euclidean space. And this is centered L's power of the Wigner matrix, general Wigner matrix. And this here we have a bilinear form. Whenever this guy, which is random, satisfies the Lyapunov condition for central limit theorem, we call it the pair satisfies the W to the power L Lyapunov. Essentially, it's like very simple term to simplify what we're trying to say. Okay, so this means once you have this definition, which means whenever you have this kind of random quantity, after certain rescaling, in the end, we see a bell-shaped curve. The question is, how do we verify this condition? Actually, there is some simple sufficient condition ensuring that this condition is true, which means there's simple condition we can work with. All right. Again, we have to live with conditions. But still, basically, this is all the conditions we need. It's something similar to what we saw earlier in the first part, so I will maybe skip. One thing is, in this work, the eigen separation in the ratio, currently we assume that this guy should be positive. But if you like, if you really feel that this is a very strong assumption, we can still relax to a shrinking number. That means we have to work harder for the mathematical arguments. Okay. I apologize that actually this slide is even messier. And so in order to understand the precise property of the eigenvectors and eigenvalues, so we have to work with some random quantities. So here basically we have in this case we have for every positive t and pair of unit vectors x, y, we define a function. By the way, this function actually is non-random. It's function of x, y, and t, and this is basically a summation, and it's a binary form, it's rescaled, and here basic expectation of the L's power of the general Wigner matrix noise. And here basically L in general is a very big number. We have to specify in the proofs. So you might guess that the reason why we introduce the quantity must be that at some point in the derivation, we have to deal with the expansions. That's indeed the case. All right. Once we have a quantity, for every k between 1 and k, the number of communities, we have defined the red number tk. What is tk? Tk is a number very close to the true eigenvalue dk. It's an interval around dk, and we have to solve this highly nonlinear equation. And it relies on notation. I cannot explain the whole picture for this one. Maybe next time I should include a picture. So essentially, put in simple terms, for every k between 1 and k, we define tk, which solves the equation, and in essence, very close to the true eigenvalues. And the good thing is, even though the equation we solve is very complex, we can prove that the tk, first, it exists. Second, it's unique, which means it's identifiable. And interestingly, the tk, the solution from the equation, asymptotically, is very close to the population eigenvalue dk. All right. Then you ask, what's special about the tk? We took a lot of efforts to introduce a notation to define the equation and find a root. In a simple term, the tk we defined actually is the asymptotic mean of spider eigenvalues. So later on, if you want to do, okay, thank you. If you wanted to do the expansion, this is basically the asymptotic mean. Okay. Naturally, we expect that under some conditions, we can prove that the imperial eigenvalue, this is the absolute mean, and this determines basically the stochastic variation. Under some conditions, we have CLT. As I just mentioned, and the real motivation for our project was trying to understand the limiting distribution of eigenvectors. So the next, I want to spend maybe 2 minutes to explain next a few slides, then I can conclude my talk. So essentially, we have empirical eigenvector. We want to ask the distribution for this one, which means because this is a very high dimensional vector, and we look at arbitrary linear combination, ut times vk. And because we know that there's two sides, right, upside or downside, so we fix the orientation, and we do expansion. And interestingly, we have to distinguish between two cases. One case is the u vector is different from the population eigenvector, which presumably is the real case because we never know this population guy. In this case, we can do expansion. The tk controls the rate, and also this is asymptotic mean, which further has this decomposition, and this is the order term, and this is basically a stochastic term. Of course, under some conditions, we can prove that the CLT. What happens if the vector is equal to the population vector. And turns out we end up with different expansion. The rate is different. You notice it's square. Actually, it's faster. And under some conditions, we also have the asymptotic normality. Okay. So what I just presented actually is some asymptotic property for a general linear combination for eigenvector. And it turns out, even if I use the term general theory, it turns out there's even more general theory beyond linear combination. So the truth actually we started with the bilinear form. X transpose times V hat K times V hat K transpose times Y. And with some efforts, which is new technical mathematical proofs, we can understand this guy. And then suddenly we can understand linear combination, eigenvalue, blah, 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 blah. Again, basically the comprehensive results will be from this the paper. I guess, do I have time's up? Or 1 minute, okay. And then I can just show a picture. Because I mentioned the asymptotic normality, which means we have to expect a bell-shaped curve. So this is the first eigenvalue, second eigenvalue. After the rescaling and centering using the results from the paper, we see very nice match. And also for eigenvectors, U1, actually this is A vector over root n. And the second guy is the population eigenvector. Third one is, oh, this is very simple because this is entry-wise. Only first guy is 1, rest is 0. But we all have this very nice bell-shaped curve. Second eigenvector, very, very similar. Okay. With that, essentially we looked at two aspects that are related. First one, how do we do inference in networks? Second one is how do we understand the properties of eigenvectors for random matrices? And this is basically two manuscripts I mentioned. At this point, we're still finalizing. So if you have any comments, suggestions, I would love to receive either offline or by email. And finally, I want to thank you for all the for the attention. Thanks.
Questions,
Jinchi, I like the talk very much. It's just one question. So usually the adjacency matrix, we assume the diagonals to be 0, and then it's not low rank anymore. So how do you fill in the gap?
It's a very good question. It's a little bit subtle. So you're right. Yeah, if you pay attention to the models and formulas I mentioned, actually, essentially in the models I mentioned on slides, actually the diagonal entries are non-zero. But with some tricks, you can deal with that. Essentially, even if, for example, real life you don't allow self loops, you can still get similar results. Yeah.
By controlling the degrees.
So which means you have to work modify the matrix a little bit before you do eigen decomposition. Yeah. Yeah. So a little subtle difference. Yeah. But it's a very important part, right? Yeah.
Thank you.
Yeah.
If there are no further questions, let's thank you. Yeah.